Okay, welcome to lesson 8.2. Today we're looking at the Cartesian equation of a line, and this lesson is specifically in R2 or 2 space. So the first thing we're going to talk about is the slope of the line. If I'm given the direction vector, and we talked about direction vectors in 8.1, so if you can't remember that, go back and take a look at that lesson. If the direction vector of a line is m, where m is equal to the coordinates a comma b, then the slope of that line is going to be m is equal to b over a. And you may have noticed that in lesson 8.1. For that to be the slope of the line, though, of course, a cannot equal 0. If a was equal to 0, then I would have a vertical line, and then the slope would be undefined. So in R2, the Cartesian equation of a line, so this is just a third form of the line, in 2 space, is ax plus by plus c equals 0. And so in grade 9 we called this standard form. What's special though this year when we look at this equation is the normal axis is involved in this equation. So the normal axis passes through the origin. I can see it here in blue in my picture. It always goes through the origin and it's perpendicular to the line that I'm looking at. So here the line is in red, and so the normal axis here is in blue. Any vector along that normal axis is called a normal vector. And if I have my line in Cartesian form, then one of the normal vectors is always going to be the coefficients of the x and the y, and they would go in the x and the y spots in the same order. So we're going to use that idea. That's always going to be perpendicular to the line, which will also be perpendicular to the direction vector for the line, because since that is parallel to the line. So in example 1, we're going to determine the Cartesian equation of the line, and we're given a point, 3, 5, and I'm given the normal vector. So when we use this notation here, n is always going to be our normal vector, and when we use the notation m, like above, that's going to be standard for our direction vector. And they're telling me that that's the normal as well. So if I'm given, remember that n is always the a, b in my equation, and I'm given that it's -2, 4 in this example, then my equation, which is ax plus by plus c equals 0, I can just sub those values right in as the coefficients. So -2x plus 4y plus c equals 0, and we're closer here, we're on our way. And just like in grade 9 math, and once we come up with those two coefficients, we can find, it used to be like the b value, the lowercase b value in y equals mx plus b, but to find this c value here, we're going to sub in the point that we're given. So here we're given the point 3, 5, so I'm going to sub that in for the x and the y, and then I'll just be left to solve for c. And so I've got -6 plus 20, so 14 plus c equals 0, and then I can solve for c. And so therefore, one Cartesian equation for this line is -2x plus 4y minus 14 equals 0. So unlike standard form, it's okay if the coefficient on x is negative for the Cartesian equation. Now, that's just one possible Cartesian equation. I could find another by multiplying or dividing this entire equation by the same number. So, for instance, if I were to divide this whole thing by -2, another version of this equation would be x minus 2y plus 7 equals 0, and that would give me the same line. So there's multiple versions as well for this type of equation. All right, example 2. Oh, sorry, I missed the bottom of that page. The bottom of this page is talking about parallel and perpendicular lines. Remember, parallel lines run in line with each other, and sometimes we use this symbol for parallel, and then perpendicular meeting at the 90 degrees, and sometimes we'll use this symbol as well for perpendicular. So we're going to be using two different lines here. We want to see how they're running. We're normally going to call these lines L1, so just a subscript 1, and L2, subscript 2, and then we'll distinguish between their two normal vectors with the same subscripts 1 and 2. So L1 and L2 are parallel if their normals are scalar multiples of each other. So what that means is that n1 would be equal to some number k times the n2 vector. And so that number k can be any real number where, of course, it cannot equal 0. So some other number other than 0. And if I can write the normal vectors in an equation like this, then I know that the two lines are parallel. This next one about perpendicular lines is an if and only if. So you may have seen this kind of statement before in math, and it's saying that the statement is true in both directions. So if I know that the thing on the left is true, then automatically the thing on the right is true, or vice versa. If the thing on the right is true, then the thing on the left is also true. And this term if and only if, you're going to see it in future mathematics courses, and we use this symbol here, the double arrow, to say that it goes both ways, this statement. And so what we have here is that L1 and L2 are perpendicular. That's what I've got here on the right. It's just flipped. If and only if the dot product of their normals is 0. So, and that kind of makes sense to us, right? We're used to talking about if the dot product of their direction vectors would be normal, and that's also true. I can see that here in the note. The dot product of the direction vectors will also be 0, but more specifically, if the normals are perpendicular, then I know that the lines are perpendicular. Sorry, if the normal dot product is 0, then the lines are perpendicular. All right, so let's take a look at an example looking at parallel and perpendicular. In part A here, it says show that the line 1, and I've got the Cartesian equation, and the line 2, another Cartesian equation, are parallel and non-coincident. So that means that they're not actually on top of each other. They are two separate lines, but they are parallel to each other. That's what I need to show. So the first thing that I'm going to do is pull out those two normal vectors. So for L1, I'm using normal 1, and I can see that the normal vector is going to be the coefficients on the x and the y, so 2, -5. And for the line 2, the normal vector is going to be the coefficients on x and y, so 4, -10. And hopefully once you got the normals pulled out like this, you can see that they are just multiples of each other. So I can come up with n2, this guy here, just by doubling what I have over here. So if I take 2 times the first normal vector, then I will come up with the second normal vector. So if you couldn't see that, what you would do is take the two x values, divide them, and see if you got a scalar multiple. Well, usually it'll come out to a nice one, and then do the same thing with the y values, and I get the same scalar multiple. And so because of that, I know that the scalar multiple is in fact 2 on this one, just in case the numbers aren't quite so nice. That's how you would figure that out. And so then I can say that I do know that the two lines are perpendicular. So since or sorry, did I say, I think I said perpendicular, the two lines are parallel. So the only thing left that I have to show is that they're not actually the exact same line. So what I'm going to do is just pick a point on line 1. So I'm going to pick an x value, find the height of it, and then same thing on line 2, pick the same x value, and I'm trying to show that the height of it will be different. So I'm just going to pick, and I always think x equals 0 is a nice easy one for me to pick, but you could pick something else as well, like maybe you want to pick x equals 1. If you look ahead for the arithmetic, it might be a little bit easier for certain x values. But I'm going to go with x equals 0. Then for line 1, I'm going to plug in x equals 0 here, and I'm left with -5 plus 2, -5y plus 2 equals 0, and I'll solve again for the height of this point. So -5y equals -2, and then dividing it out, I'm going to get a positive and 2/5. So now we're going to check for x equals 0 what's happening on line 2. So on line 2, I'm plugging in x equals 0, this term goes away, and I'm left with -10y minus 3 equals 0. And again, I'm solving for y here. And you can probably already see it. This is not the same height. And so that shows me that these two lines are parallel but not coincidence. They have at least one different point on them, so they can't be on top of each other. All right, we're going to take a look at example 3 here. It says determine the acute angle to the nearest degree formed at the intersection of, oh wait, sorry, there was a part B to that question. For what values of K are the lines L3 and L4 perpendicular lines? So if I want to show that two lines are perpendicular, I want to check the dot product of their two normal vectors. So the first thing I'm going to do is pull out the normal vector of L3. It's going to be 2, negative 5. And the normal vector of L4 is going to be K, 4. And so then the question asks me, what is the number that I need to put in here? What's the value of K so that I end up with two perpendicular lines? So if the two lines are perpendicular to each other, then the dot product of the two normal vectors will equal 0. And so we're going to figure that out. Remember, to do the dot product, I multiply the two x values, so 2 times k gives me 2k. And then I'm adding, multiplying the y values, negative 5 times 4 gives me negative 20. And then I'm going to solve this for k. And so therefore I can see that if L4 is 10 for the x coefficient, plus 4y minus 5 was the rest of the equation that was given to me, then the two lines will be perpendicular. All right, the next one here, example 3, we're determining the acute angle to the nearest degree formed at the point of intersection. So I'm just going to highlight that word acute. It tells me that my answer does have to be between 0 and 90 degrees. So I'm just keeping that in mind for the end of the question. If I'm finding the angle between two lines, then I'm going to look at their direction vectors. And remember, the direction vector from yesterday is the vector that's being multiplied with the parameter. So this guy and this guy, those are my two direction vectors. And remember back from chapter 7 that if I take the dot product of the two vectors, I can find the angle in between them. So I'm going to use that same idea here. So for L1, I come up with the direction vector 2, negative 3, and for L2 I come up with the direction vector 5, 1. And what I want to do is take a look at the dot product of those two. Oops, 1 and 2. I know that the dot product is equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle in between them, and that's what I'm looking for, right? That angle there. So we can rearrange this. We did this a lot last unit. We're going to take the two magnitudes and divide it out on the other side. At the same time, I'm just going to switch the sides here. So we're going to say cos theta is equal to the dot product divided by the magnitudes. You can do these calculations off to the side if you want, or you can do them all within this calculation here. If I'm taking the dot product of these two vectors, I'm multiplying the x values together, so 2 times 5 gives me 10, and then I'm adding, multiplying the y values together, I get negative 3. And then on the bottom, we're going to square root the sum of the squares of the components. So 4 plus 9, and then squaring these guys here, I get 25 plus 1. It's a plus. And so what we get here is 7 over root 13 root 26. And remember that I'm solving for the angle in between them. So I'm going to bring the cosine over and do cos inverse of all of this stuff. Make sure you type this into your calculator correctly. So now's a good time to practice and make sure that you know how to use that. Make sure that you're dividing out the right numbers here. You should get about 68 degrees if you're rounding to the nearest whole degree. So there's a rounding symbol there. Now, remember at the beginning of the question, they asked us to determine the acute angle. So I wanted my answer to be between 0 and 90. So here I got an acute angle, so that's lucky for me. But if in a question I got a number that was bigger than 90, all I would have to do is subtract that angle. It means I found the obtuse angle between them. So I would just subtract that angle from 180 degrees to find the acute angle. Just one thing I wanted to point out as well, that remember whenever you have a question with two different lines, if you're doing a vector or a parametric equation, I mentioned this in the last lesson, I do have to use two different parameters. So here the parameter is s and here the parameter is t. So just make sure you make a note of that. All right, have fun with the homework.